In part 3 of section 4.1, we're going to find the extrema, either on an interval or just in general without an interval. If you are asked to identify the absolute extrema of a function on an interval, we are going to use the candidates test. Now, before we get started, if you have not yet watched part 2 to understand how to find critical points, please go back and view that video. The first step of the candidates test, which is going to find the absolute extrema on an interval, the first step is to identify all the critical points. We have already identified that the critical points here is actually only one of them, and that is x equals 2. That's our critical point. Since we are working only on the interval from -2 to 4 inclusive, meaning it includes those endpoints, we want to ensure that our critical point, or points, if we ended up having more than one, are on that interval. Is 2 in this interval? Yes, it is. The next step of the candidates test, once you've found your critical points, are to simply list all the candidates. The candidates are the values of x that are in the running to be the absolute maximum or minimum values of our function on that interval. The candidates are the endpoints and the critical points. So in this case, our candidates, which are simply the x values in the running for being the absolute extrema, are the endpoints and our critical point. I'm going to list them in order from least to greatest. So our candidates are the endpoint -2, our critical point 2, and our endpoint of 4. You are always going to have at least 2 candidates because this candidates test needs to include both of the endpoints, so you'll have 2 of them. You may or may not have a critical point, and even if you do have a critical point, it may or may not be within that interval. So you will at least have 2 candidates. In this case, we have 3 because our critical point was in the interval that we are dealing with here, between -2 and 4. Lastly, we perform our candidates test, which means since we're looking for the absolute maximum and absolute minimum value on this interval, we need to figure out what the y values are at each one of these 3 x values to identify which one's the tallest and the shortest to be given the title of absolute maximum and absolute minimum, respectively. So we can make simply a t-chart here, plug in -2, 2, and 4, our candidates, and then we can figure out what the f of x values would be for each one of those points. Using my calculator, or just kidding, I did it all in my head really fast. We get these 3 y values out. So we can clearly see what the maximum point would be on this interval and what the minimum point would be. Our maximum point, our largest our y value rather, occurs here. So our absolute maximum is 33, again on this interval, and it occurs at x equals -2. Similarly, since our lowest y value is 1, our absolute minimum is 1, and that occurs at x equals 2. I took a look at Desmos just to make sure what we're doing was correct. And obviously this function is defined everywhere and goes everywhere, but if you can look, I made the coordinate point -2, 33 bolded like with a dot, and same thing with 4, 9. And so that's the interval that we're looking at. We're not looking to the left or right of that interval. The endpoint at -2, 33 is where our absolute maximum occurs, and our absolute minimum occurs here at 2, 1. So again, only on this interval from here to here. And this right here, 4, 9, is only a relative maximum, but the candidates test is not going to, our candidates test is to find absolutes on our graph. We would have to graph it or use other measures in order to find relative. But on our interval, because this function is continuous on the interval from -2 to 4, the extreme value theorem states that it has an absolute max and an absolute min. We found the absolute max at 33, occurring when x is -2. The absolute min was 1, occurring when x is 2, and we found those using the candidates test. In number 2, we want to again really do the same thing. So find all the absolute extrema of our function on our interval. In this case, our interval is from 4 to 10 inclusive. This is just a different way to write an interval. So we need to use the candidates test because we're asked to find absolute extrema on an interval, which is what the candidates test will tell us. So our first step is to find the critical points. We found the critical points of this function in the previous video, and we found that those critical points were -3 and 3. So our critical points were -3 and 3. However, neither one of these critical points are in our specified interval. Since these critical points are not in the interval, they're not going to be candidates. Candidates, recall from the first example, are the endpoints and the critical points if those critical points are within our interval. So in this case, our candidates are simply just our endpoints. Again, because the critical points that we found in the previous video were only -3 and 3, and those are not in the interval from 4 to 10. So our candidates are only our endpoints. In this case, are x equals 4 and x equals 10. Candidates are in the running for being the absolute minimum or absolute maximum on the interval. They are candidates, and so we have to test them in order to see which is which. Performing the test looks like creating a t-chart with all of our candidates on it and their respective outputs. We only have 2 candidates in this case. When we plug in 4 to our function, we'll have 16 minus 9, the square root of 7 in this case. Then when we plug in 10, we'll have the square root of 100 minus 9, or the square root of 91. The y values, or the g of x values here, our outputs, tell us the height of our function at that particular x value. So the taller of the two is the square root of 91. Therefore, right here, the square root of 91 is our absolute maximum on that interval from 4 to 10, and it occurs when x equals 10 at our endpoint. Similarly, our absolute minimum on this interval is the square root of 7, and it occurs at the endpoint x equals 4. Because our function g of x is continuous on this interval from a to b, in this case a is 4, b is 10, the extreme value theorem guarantees that we have an absolute maximum and an absolute minimum on that interval. In this case, they happen to be at the endpoints. We found that using our candidates test. In our third example here, this is one, once again, that we looked at in part 2, finding critical points. But this function here, we are looking at the interval from 1 to 5, and we want to identify again the absolute extrema of f of x on this interval. So in order to identify absolute extrema on an interval, we need to perform the candidates test. Our first thing is that we need to find the critical points. In that video, we found our critical points to be x equals negative the square root of 2 and positive the square root of 2. Of course, these critical points don't mean much if they're not in our interval. So we want to see if our critical points are in the interval from 1 to 5. Well, the square root of 2 is slightly larger than 1, so the square root of 2 is in the interval. However, negative numbers are not a part of this interval, so negative square root of 2 is not in the interval. Therefore, the only critical point that is a candidate would be positive square root of 2. So next step is to list all of our candidates. Candidates, recall from the previous examples, are the endpoints of our interval and any critical points that are in the interval. So our candidates here, we have 3 of them. Listing them in order from least to greatest would be the endpoint 1, then the critical point positive root 2, and then the second endpoint, not a root, of 5. These candidates are the x values that are in the running to be the absolute extrema, either the absolute maximum or absolute minimum. The way we determine which they are is we have to see their height or their y value on our function. So we have to plug them into our function to see which is the tallest and which is the shortest. Now here I use my calculator. Well, I didn't for the first one because we have 1 over 1 to the 4th, which is 1. Plus the natural log of 1, which is 0. So our output here is just a 1. I plugged into my calculator the next two, and I got 0.596. And then for plugging in 5, I got 1.611. Now we can see which is the tallest or lowest point of these three candidates. We can see that our highest number, our highest y value, is the 1.611. So our absolute max on this interval from 1 to 5, the absolute max is the y value, it's the height, 1.611, and it occurs at the endpoint of 5, at x equals 5. Similarly, oops, not there. This is the smallest number. Our absolute minimum is this decimal, which is 0.596, and it occurs at x equals the square root of 2. This next example looks slightly different than the previous ones we did, and that is because we are asked now to identify all the relative extrema, not solely to identify the absolute maximum and absolute minimum, and in this case it's different as well because we do not have an interval. Because we are not asked to identify absolute extrema on an interval, we're not going to use the candidates test anymore. Instead, we're going to use what's called the first derivative test. Similar to the candidates test, the first step is actually the same, and the first step is to identify the critical points. I'm going to quickly go through the critical points once more, even though we already did this in the previous video. Remember, to find the critical points, we find the first derivative, set it to 0, or find where it's undefined. Our first derivative is the following polynomial, using the power rule, and then setting it equal to 0, and factoring, we get 3x squared plus 6x minus 4x minus 8, because 6 and negative 4 multiplied to negative 24 and added to 2. Then we factor by grouping, by pulling out the GCF of the first two terms, and then doing the same thing with the last two terms. Then we end up with the GCF of x plus 2, and what remains is 3x minus 4. Setting each one of these to 0 yields the two critical points of negative 2 and 4/3. I went through that more in depth in the second video. So we found our two critical points, x equals negative 2 and x equals 4/3. No need to see if they're in an interval because we are working with all real numbers at this point. No interval was given. The next step in the first derivative test is to then create a number line in order to see whether our derivative is positive or negative in certain intervals. This number line will look just like this and will tell us the x values that we care about as well as the sign of f prime. So the x values that we want on this number line are the critical points, so negative 2 and 4/3. And we want to know what's happening with the first derivative, which is up here, at those points. Well, we know that if we plugged in negative 2 or 4/3 to our first derivative, they would output as 0 because we set our first derivative to 0 when we got these x values. So if we plugged in negative 2 or 4/3 into our first derivative, we'd get a 0. That's why they're critical points. But what we care about really is not so much f prime at those points, we know it's 0. We care about what the first derivative is here, here, and here. Because if our first derivative, let's say, is positive and then negative, that means our function was going up and then going down, meaning negative 2 would be a relative maximum. Or rather, if our first derivative is negative and then positive, that means our function was decreasing and then increasing, meaning this value would be a minimum instead. That's what the first derivative test tells us. So what we need to do is pick a number in this interval, and this interval, and see what the output f prime is. Is it a positive number or a negative number? The first number I'm going to plug in will be in this interval here, where x has to be less than negative 2. I'll pick negative 3. Now, f prime is written out up here as a polynomial in standard form. It's also written here in factored form. I like it more in factored form, so what I'm going to do is rewrite f prime just in this factored form that we found because it's easier to plug numbers into a form that looks like this. Remember, we don't care really what the output of f prime is as a specific number. We care about whether the output is positive or negative. So if I plug in negative 3 into f prime, Here's what you really need to think. We're really thinking of it like this. That's a little thought bubble in case you couldn't tell. So plugging in -3. Here, if we plug in -3, we get a negative number. Here, if we plug in -3 into this parentheses, we also get a negative number out. Therefore, our output here, plugging in -3, was a positive because it was a negative times a negative in those two parentheses. So we're going to put a plus sign here because any number that we plug in this interval here gives an output of a positive first derivative. That means that our function, our original function, is increasing on this interval because the first derivative is positive. Next, I'm going to plug in a number in the next interval. The next interval is in between -2 and 4/3. Anytime you have an interval that goes from negative to positive, you know the number 0 is smack dab in the middle, and 0 is super easy to plug in. So I'm going to plug 0 into f prime now, and here's my thought process. When I plug in a 0 here for x, we get a positive number, which is just 2. So it's a positive number. Then if we plug a 0 in here, we have -4 as our output, or a negative number. A positive times a negative yields a negative. So our derivative is negative between -2 and 4/3, meaning that our original function f of x was decreasing here. The last value that we can plug in is some number over here, and I'll be ridiculous about it and plug in 100. When we plug in 100, or any number of your choosing that's greater than 4/3, we'll clearly get a positive and a positive in both factors, yielding a positive first derivative. What does this mean? Because our first derivative goes from positive to negative to positive, that means our original function was increasing, then decreasing, then increasing again, changing from increasing to decreasing at -2, and changing from decreasing to increasing at x equals 4/3. That means that -2 and 4/3 are relative extrema because it's where our function changes from increasing to decreasing or vice versa. Here's what our original function looked like. It increased, then decreased, then increased again. And here's where x was -2, and here's where x was 4/3. I don't know what their specific y values were at these points, nor do I know if the function looked exactly like this. I highly doubt it. However, we do know that the general shape of the function was increasing to decreasing to increasing. Because of this, because our function went from increasing to decreasing at -2, because our first derivative was positive and then negative there, we know that -2 is a relative maximum point. For similar reasons, we know that x equals 4/3 is a relative minimum point, because our first derivative went from negative to positive, meaning our function decreased then went back to increasing. We know that we had a relative maximum at x equals -2. We also know that we have a relative minimum at x equals 4/3. Now, can we find that maximum and minimum? Yes, we can find those values by plugging in -2 and 4/3 into our original function f of x. That'll give us the height of the function there, or the y value. In general, here's how we can make these conclusions. We have a relative maximum from our first derivative test if our first derivative goes from positive to negative, because that means our function increased then decreased at that point. A relative minimum occurs when our first derivative goes from negative to positive, because our original function decreased and then increased at that x value. In this last example, we once again want to identify all the relative extrema. Because we're asked to identify all relative extrema, and we are not given an interval, what we want to do is perform the first derivative test. The first step of the first derivative test is to find all the critical points. This is not one that we looked at in the previous video, so I will go through finding the critical points. In order to find the critical points, you need to find the first derivative. Since this is a quotient, we'll do the quotient rule. Low times d high. Well, the derivative of the numerator, d high, is 0, so I'm not even going to bother with low d high. Minus high d low. All over low squared. Cleaning this up, we'll get -2x over x squared minus 1 quantity squared. You can just leave it like that. We don't need to worry about squaring that and possibly messing up the algebra. The next step is to find the critical points, is to set the first derivative to 0, or figure out where the first derivative is undefined. When our first derivative is a fraction, in order to find where that fraction is 0, we simply set the numerator to 0. So we are going to set negative 2x to 0 to get the critical point x equals 0. Then we want to set our denominator to 0 to figure out where our first derivative would be undefined. So we are going to set x squared minus 1, quantity squared, equal to 0. We'll square root both sides, add 1, and take the square root. Therefore, our three critical points are negative 1, 0, and 1. So we have found our critical points by setting our first derivative to 0 and figuring out where our first derivative is undefined. When our derivative is a fraction, that means it's 0 when the numerator is 0 and undefined when the denominator equals 0. Our next step is to create a number line using our critical points. So our number line will look just like this and have our critical points on them. The bottom part of the number line is x values, and the numerator tells us what our first derivative is, positive or negative. Now we do have to be careful here. Our first derivative is not 0 at negative 1, nor is it 0 at 1. It's actually undefined. So what I'm going to write instead is this little, our first derivative is 0 when x equals 0. Now what we care about is the sign, positive or negative, of our first derivative, and I accidentally put f, it's technically y, not that it matters that much. We care about the sign of our first derivative in this interval, this interval, this interval, and this fourth interval here. Now, this one can be done really fast. Again, we don't care about the actual number. We care about if it's positive or negative. So let's plug in a number that to the left of negative 1 over here. I'll say negative 10. If we plug in negative 10 for x, we'll have a negative 2 times a negative 10 in the numerator, giving us a positive output. So we're testing x equals negative 10 here. Then, no matter what we plug into this denominator, we square it. So as long as we're not plugging in negative 1 or 1, which would make it 0, which we're not, anything that we plug in down here ends up being squared. So it's always positive. So this is always positive down here. So we're going to keep that positive down there. All we really have to test now is the numerator. Positive over positive is a positive output. The next number that we can try needs to be in between negative 1 and 0. We know that that's going to be a negative number in there no matter what it is. So a negative times another negative here is going to again be a positive value. Then the denominator is always positive, so this is a positive here. Now between 0 and 1 is our next spot that we have to test out, which we know it's a positive number, whatever we plug in here. A negative 2 times any positive number is going to be negative. Since the denominator is always positive, a negative divided by a positive is a negative. We can again use that same reasoning for 1 to infinity, whatever number we plug in there. So the number line section does not have to take you too long, as long as you can sort of use some reasoning and logic when plugging in your values. If you end up plugging them in every single time, it can take you a very long time, but you can start to use the ideas of, hey, if we're squaring something, it's always positive, those types of shortcuts in order to get this quickly. Now, our last step is to conclude from the information that we've got here. What we care about is when we have a change in sign of our first derivative. If our first derivative goes from positive to negative, we had a relative max. If our first derivative goes from negative to positive, we had a relative min. The only time that we have a change in our first derivative is at x equals 0. We did not have a change in our first derivative at negative 1, nor did we have a change in the sign of our first derivative at 1. Therefore, negative and 1, even though they're critical points, are not relative extrema. 0, x equals 0, is a critical point and ended up being a relative extrema in a sense that it is a relative maximum because our first derivative went from positive to negative. So we can conclude that a relative maximum occurs at x equals 0 because f prime of x went from positive to negative. Here is a Venn diagram that I created about the differences between the candidates test and the first derivative test to find extrema. The candidates test is used to find absolute extrema on an interval, whereas the first derivative test finds relative extrema and does not have an interval. The candidates test uses a t-chart to find the y values, while the first derivative test uses, I called it a number line, it also is referred to as a sign chart, since we use plus or minus signs on it, whereas the t-chart does not use that, it uses the actual y values. And the candidates test involves the endpoints because it's on an interval, whereas the first derivative test doesn't. Can you think of what they have in common? They both use critical points, which is why I have a separate video for finding critical points. They are very important with applying our derivatives. So both of these allow us to find extrema as well. So I will also put that in the center. Be sure that before you are asked to find extrema, you understand which test you are going to use and why.